All right, so why don't we explain this real quick before we get started?
Yeah, so you might be wondering why this isn't a video and it's a podcast, and it's just because it's not because we're lazy, don't want to make a video. We just think that it took a really long time, and we feel that it would
It's already closer to a podcast in nature, and
when you're producing a product, you want to you want to make the medium enhance it. So we feel that if we made part of the experience having to watch a video, it would be less enjoyable than just listening to it, because it's just so long
and so talky and so
talkative. So that's why we're presenting this in the form of a podcast. It may not be like this next week, but this is just such broad of a topic that it took a long time, and we hope that you're satisfied with this. And
so sometimes it won't be like this. Sometimes it'll be us vlogging almost, and
enjoy it.
These will just be different. They'll be varied.
Sunday afternoon.
Yeah.
Sitting down, grab a drink, relax, and let us talk to you for an hour.
Yeah, about an hour probably.
Practically unedited.
Yeah.
So be having a good experience. That's all.
That's the Henry promise.
That's the Henry seal of approval.
We could record this in the dark next time.
Yeah, we could.
Well, assuming it's a podcast, assuming we do a podcast style again. Handshakes. There we go.
Wait, what? That was a good handshake.
It was?
That was an above average handshake.
Oh, I thought that was awful because I went too deep.
No, you gotta go too deep.
What? Okay, what I like to do is I like to get a handshake like this.
This is also a sidebar. Open up your hand like this, and I like to interconnect the web, but not do too hard. You see how I'm hardly...
I just don't like that though because it feels too tight. This is my kind of handshake right here because then I can get your web right there, but it still feels like...
Yeah, but you see, it feels good for you, but I'm hanging out to dry over here. Look at
you are? Oh, well, I expect them to... imagine the same... Okay, do that same thing you're doing there, right? You're gripping me tightly?
I'm not even gripping you at all.
You're not?
No, I'm not at all. I'm not gripping you at all.
Are you being sarcastic?
No, I'm not even kidding. This is how much I'm gripping you. This is no exaggeration.
Okay, because when I do it, I'm exerting some muscle here.
I'm exerting zero muscle.
Okay.
Connect the web, exactly.
It's kind of forcing to exert muscle.
But it's just a feeling of tightness.
Yeah. Then again, muscleness, the feeling of exerting a muscle is really just tightness. You're feeling tightness.
No, it's just physics. It's not your muscle. It's doing the action.
I know, but I'm saying when you feel, you're flexing your muscle, you're really just feeling tightness.
That's the feeling. Yeah, it has the same.
So it's the same.
A similar feeling,
exactly.
Except it's a lot more just relaxed on either party.
Yeah, that's not the handshake I ever go for.
That's always.
But it always ends up
happening. I do a
happening.
handshake 4 times a day.
Why?
I'm not even kidding. That's my primary mode of greeting people. Handshaking would not be invented without society. And society would not be inventing without farming. Today, on the inaugural episode of The Wash, we will be explaining...
Inaugural?
Yeah.
This isn't an election, Henry. It's a...
No, inaugural is the first.
Is that what... Oh, I've always just heard it used in reference to elections.
On the inaugural episode of The Wash, we will explain the history of farming and modern farming, especially ammonia.
Big A.
Big A. Let's begin. So farming arose...
Okay. Make it less presidential.
Oh, okay.
Turn it down just a little bit.
So farming arose 8 to 6,000 years BC ago. We don't know, but it's around that time due to fossils that we found. Archaeologists.
So find fossils of seeds arranged or something, in a pattern.
Yeah, actually, I was reading this book about Gun, Germs, and Steel by Jared Diamond, and it's about human geography, and he explains how they find different seeds. They can map the civilization just by the seeds they find in things poop that has been fossilized, because they can mark its anyways. 8,000 to 6,000 years ago, BC. It rose around independently
One second, let me turn off the volume of my computer because otherwise my friends' notifications are going to be ridiculous. Alright.
So it rose independently across the entire world, including the Indus Valley civilization, which the Harappan civilization, the first Indus Valley civilization, the Xian dynasty in China, which is the first Chinese dynasty.
I feel like you pronounced that wrong.
No, I actually wrote the exact pronunciation.
Wait, really?
Yep.
Oh, Xi'an.
And the Mesopotamian River Valley civilization, the Sumerians, and the Nile, which is the proto-dynastic period. They all
Proto-dynastic. Whoa, let's talk about that. What does that mean? What does proto-dynastic mean?
before dynastic, before the dynasties.
Oh, of China?
Like, no, of Egypt. There's the New Kingdom, Old Kingdom, or, dynasties.
Oh, okay.
New Kingdom, Middle Kingdom, Old Kingdom, and Proto-Dynastic.
Proto-dynastic.
I've always had a fascination
I
with...
should name my kid Proto-dynastic.
No, you should name your kid Thebes.
Shut up, okay?
That's camera
Thebes.
stuff.
Hmm?
Well...
I need to turn this down, too.
you might be wondering...
Just one second. I need to turn this down. Otherwise, it's going to create problems also.
All these civilizations are located in Eurasia, Afro-Eurasia, meaning the continents of Africa, Europe, and
I don't
Asia.
think you need to explain that.
Afro-Eurasia. None of them. No societies developed independent farming in North America or South America. We can explain that in a future video with the link here.
Henry, you realize that video is not going to exist for like a really long time.
It'll eventually exist. Anyways,
Okay.
farming made food surpluses, which led to specialization, because people had to count it and produce it and govern it and distribute it. And that counting it led to the origin of math, and people made stronger tools
Just
to farm.
All math,
That's where it originated from.
just from counting food.
Yes.
Is that also how we got like zero and all those other advancements in the decimal system?
That eventually came. That's more theoretical, but counting itself originated from harvesting things, and addition and subtraction came from the politics of collecting early crops. It also led to development of science and technology, like bronze for better
for farming.
For tools. Yeah, because when people settled down to farm, they were able to specialize and form early governments. Also, surpluses allowed for trading between countries or early societies, because when you have a lot of food and they have goods, that's how that works.
You can only trade when you have extra.
That's true. So, however, that doesn't mean farming is natural. I mean, to quote Charles Darwin, he said it was by accident. He said it was just, we happened to be, gathering bushes, and, one day we saw, put them in order or something like that.
Just thinks. Okay, I think that's I think we probably did farming on purpose. It's not that complex of an idea, right? I feel maybe it's just because we know so much about plants
But
nowadays.
Anyways, farming did allow for centralized populations, but that caused disease and slavery, because of course, with society, slavery comes. That's just how it works. Farming is very difficult. You may or may not know, and when things are difficult, I consider owning another person.
Of course.
So, yeah.
That's how I get rid of all my troubles.
Interestingly, certain historians point to farming as not improving the health or creative aspects of life that hunter and gatherers have. They said that they had more time to work and create art or complex things like that when they were hunting and gathering, which is interesting. And they had better health. So 78% of the atmosphere is nitrogen. Diatomic nitrogen, not ammonia. So diatomic means...
if the 78% of the oxygen... Sorry, the atmosphere was nitrogen.
We'd be dead.
Yeah, we'd be dead.
But, diatomic, that means that it's just nitrogen bonded to nitrogen. And it's a triple bond.
Gotta pump. We need to have more energy.
See, none of us have energy. We don't have energy.
I have energy. I'm
You're
waiting. Yeah, I was making fun of you.
I was just kind of thinking of this as a podcast right now. Just trying to have a more soothing voice.
All right. Well, then try. Oh yeah. Also, I want you to try talking more to me. All right.
Anyways, back to the grill again. The triple bond of nitrogen has. It's a very strong bond. It's triple bond. There's no free electrons, so there's.
Strong bond.
It's not going to bond to anything. It's going to take. It's not even.
It's really strong bond. It's not funny to you?
No, has no free electrons, so
Okay.
it basically it's unreactive, and
Right, because you need free electrons to do the whole
reaction
rigor
thing.
mortis.
Yeah, so basically, the plants and animals need nitrogen, and because it can't be worked with in its diatomic state, the hard to bond
Right.
state, it's broken down into ammonia, NH3, a compound containing nitrogen and hydrogen.
It's broken down into ammonia?
Or it's
Wouldn't it be like
It's
made into
it's
ammonia?
reacted.
Yeah.
So that's it's much more reactive, and both plants and animals need it. It's provides the structure for amino acids in animals, which provide the structure
Everything.
of protein, and in plants it is a component, the main component in chlorophyll, which is what allows it to trap the sunlight,
Yeah.
produce energy. The animals eat it. And so that brings us to the nitrogen cycle. And basically with the nitrogen cycle, the animals, or the plants get the nitrogen in the chlorophyll, and then they get the sun's energy, turn it into food, they survive. They get eaten by an animal, who then has the nitrogen in its protein. Then the animal,
And it's protein?
yes,
Oh, yeah. Okay.
dies and farts and decomposes, and the farts does contain nitrogen, puts it back in the atmosphere, puts it back in the soil, for it to be decomposed back into ammonia. Plants consume it, and that's the cycle. So basically, what Fritz Haber did, who is the guy who invented nitrogen fixation, he basically figured out how to do this without. He basically figured out how to make this process happen without the cycle. Just skip straight to the ammonia, so you don't have to have it being broken down through this cycle. And so it required a lot of heat and energy, 500 degrees Celsius.
Guessing to break up that nitrogen?
Yeah, and to break up the triple bond.
Yeah.
And then it combines with the hydrogen. 200 atmospheres of pressure. That's exactly
How
what
do we
you
even make that much pressure?
It's exactly what you're thinking. 200 times the atmospheric strength, plus a catalyst like uranium.
Uranium is a catalyst?
In this, yeah.
What even makes something a catalyst? I mean, I know
Basically,
heat is.
it lowers the
Well, I know it lowers the activation energy, but I mean, like, how?
I don't know.
How do catalysts work? That's the question. But I know I'm just gonna get a ton of stuff about activation energy, so.
That could be in our next video.
Yeah.
But it's pretty much it's an equilibrium reaction. So that just means that you can produce a ton more. It would be super inefficient to be producing this stuff under normal temperature, standard temperature and pressure. So if you add tons of heat and pressure to the reactant side, it'll favor the forward reaction, which means it'll produce a lot more product. The only problem is that it's extremely explosive, and that will carry on to Taji's side after these sponsors. Mattress
Blue Apron is a homegrown grassroots organization that has been shipping millions upon millions of homegrown products to soy boys across the entire United States. To
All right, but
BuzzFeed lovers.
let's hear what you have to say.
Are you done?
Yeah, that's it.
Oh. Okay. So, ammonia is actually a weak base. Ammonia reacts with water to produce ammonium ions, which is just ammonia that accepted hydrogen, and hydroxide ions, which is just water that is lost and the hydrogen. Since, like I said, the ammonia took it.
The hydroxide is OH with a minus charge, and the hydronium is H3O with a plus charge.
And a strong base would have these hydroxide ions inside them, and then they would come out when you put it inside water. So this is actually the difference, as ammonia makes the hydroxide, but never actually had the hydroxide inside of it. And so that's why it's a weak base. And this reaction
by dissociates, that's what Taji means.
So this reaction is reversible, and about 99% of the ammonia is actually still present as ammonia and does not react. So like if you were to just put ammonia in solution with water, you'd see that most of it would not react. And which is also why it's a weak base. But despite this, ammonia really does like to dissolve in water. So it doesn't react. Most of it doesn't react with the water, but a lot of it will dissolve with the water. And that's because of hydrogen bonding. Both the water and ammonia are also polar molecules, so it's really for two reasons. And
hydrogen bonding is just, well, I mean, it's pretty self-explanatory, but just when two hydrogens on two molecules will bond, and it'll form an extremely loose connection. That's like surface tension on water.
It reacts with acids to form a salt, like all bases do. And when mixed with oxygen, it actually burns a yellowish green. So this yellowish green color is because of the nitrogen. So nitrogen by itself actually burns a yellowish color. And so when you burn ammonia, the nitrogen inside splits off and it becomes that yellowy color. But additionally, remember how there was hydrogen?
Talking to me.
Right. But additionally, how there was hydrogen, remember? That hydrogen, well, actually, since it's hydrogen burning, effectively, right? Because the hydrogen and the nitrogen split off, you make water. And so...
just like in regular combustion.
Exactly. And so there's also this really cool experiment, because remember I said it forms a salt with it. You can take some ammonia, it's a gas, and you take some hydrochloric acid, right? And then you'll just put them next to each other, and then in the middle you'll start to see this salt sort of form. You get this gas, almost like dust, that'll form in the middle, and then on surfaces nearby you'll have all this salt.
And again, you could do that with any acid or base.
Right. It's just kind of a cool experiment that I saw. And then also, if you were to put some alkali metals, heavier alkaline earth metals, and some inner transition metals, and you were to dissolve those in some ammonia, you'll actually get this deep, deep blue. And it's because of something called, let's see if I can do this, ammoniated electrons, which absorb visible light. And so that's just a cool little thing. I mean,
it gets blue. Reminds me of the Chernikov effect.
Yeah, it's actually exactly what I thought, but it's definitely different.
Oh yeah. Wait, make it blue, gets blue, makes it.
What? What's up?
It absorbs visible light to make it blue?
Yeah.
It just absorbs certain frequencies though, right?
Yes. But a lot of it absorbs a lot of visible light, which kind of makes it look bluish. If you put enough in there, it would start to look blackish, I'm pretty sure. Blackish, remember that show?
That was a bad show.
Yeah, looking back, it was a pretty bad show.
It's like on par with the Goldbergs.
Yeah. And here's a cool little thing. It's not actually flammable or explosive. It's not. Not to the same degree that, I don't know, wood is, right? Because when you just... One second, my dad's calling me. It's flammable, right? It's actually not that flammable. So wood will burn at 400 degrees Fahrenheit, right? Ammonia doesn't burn until it reaches about 1,200 degrees Fahrenheit. And it only burns at about 16 to 25% concentration in air.
Well,
so it's not actually that flammable.
When you're doing the Haber process, and you're burning it at 500 degrees Celsius,
which is about the same as 1,200 degrees Fahrenheit, and then people like to say it's explosive, but it's actually not that explosive. If you were to, what's happening is a lot of the situations that it's in, it's really compressed. And then if you heat it up to that high temperature, like I said, it'll explode because it's really compressed.
Oh, yeah.
And of course, it smells bad, and we're gonna put a picture of the structure, which I believe is just pretty much like three dangling.
It's NH3.
Yeah,
It's just a
hydrogens and one nitrogen. And
nitrogen in the middle, 3 hydrogens, and then there's 1 free. That's why it's reactive, because there's a pair of electrons. There's, that there are 4. It could be NH4, which is ammonium. Ammonium is unreactive also, because it's a nitrogen bonded with 4 hydrogens. But since there are 3, there's an extra.
There's a valence electron.
Pair. There's 2. Yeah.
And now I'm going to talk about how it helps the soil. So first off, like Henry said, it's already in the soil, right? And it's a source of nitrogen, like he also said. But the way they actually get it into the soil nowadays is they take it, they like put a pipe down into the ground. I'm not joking, and they blast, like they hose down this like extremely compressed liquid ammonia, which how it's normally a gas, right? And they basically put it underground, and then it like explodes out, and then it expands underground.
You're making me hungry.
Really?
I think I was already hungry.
Oh. But yeah, and then it explodes out underground, and then it's immediately taken in by the soil and all the plants, which is a lot better than most other kinds of fertilizers, since it normally takes like a day or 2 and weeks or sometimes, and microorganisms have to digest it, and it's just not great.
Right. Naturally, it would take hundreds of years.
Right. And then typically when you hear about it in school, it's like they talk about the Haber process and how it's made. You already talked a lot about that, and you also hear a lot about the history behind it, like you also said.
Mm-hmm.
I'm going to talk about some of the downsides. So, first off, it's pretty explosive, kind of. Like I said, it's not too explosive, but in the situation that it's stored, they like to keep it in liquid state, right? Which is extremely compressed, which is explosive because of how compressed it is.
Yeah, it's an explosive compound.
And so, yeah, and also, if you might have heard about, you remember that Texas incident? Remember in Texas?
The Texas incident?
Okay, with ammonia.
No.
Like a huge ammonia thing exploded, and like I think 160 people got injured, and a couple people died.
Yeah, that's what tends to happen.
Because it's just explosive.
I mean, because you have
stored.
it really under extreme pressure and under extreme heat, so if you don't do it perfectly, it'll explode.
Mm-hmm. And that, also part of how it's made involves that. And also, it's not great because it's like highly toxic, because it reacts with water.
Yeah, you've all had your fair share of intimate time with ammonia.
Intimate time with ammonia. Don't ever have intimate time with ammonia.
When you're those lonesome nights cleaning your sink.
Not a whole lot of people have died from it, but you can die from just too much ammonia, like inhaling it, because, like I said, it reacts with water.
Go home, check your drain cleaner, check your sink cleaners, stain removers. Guarantee it. Ammonia, like 10% or less.
You done?
Yeah.
Okay.
Just giving them a little homework assignment.
Okay. So yeah, don't breathe it, because it'll fucking kill you. Oh wait, shoot.
We can just leave it up.
Yeah.
We're not gonna get people. For all of you who are left listening now, I know it's been an ordeal.
Yeah.
You've made it. Let's just give you a round of applause.
Okay.
That's right. You have the seal of approval.
Oh, and don't drink it. I mean, it would be hard to drink it because it's a gas. But if you think you can drink fluids, then you can drink it.
Let's see. Where are you on this list?
There.
Oh, okay. So we're just gonna quickly go through the uses. Have our.
Whoa. Okay.
Okay, we're gonna quickly go through the uses.
Uses.
Wrap it up nicely for you. Hopefully you've learned something. But before we end, let's talk about that.
So, just don't do it. And also, if you did ingest it,
we're still on this one.
I just wanted to talk about this real quick. You get it does affect the central nervous system, and it causes shock and convulsions. It's pretty good.
I would expect that.
Really?
Yeah.
Why is that?
Convulsions.
That does not answer my question. Why would you expect that?
You get convulsions when you consume a toxic chemical.
I don't associate toxic chemicals with convulsions.
I do.
Why? Have you...
Like that.
Oh no! He's got the bad A! Alright. So it's a pretty cool fuel. Pretty cool fuel.
Makes sense since
Although it burns hot. So I don't know why I said cool. Yes.
Alright.
Yes. Yes.
Fuel gas, basically the same thing.
But it's not great if you were to put in like a diesel engine because it's got like a third the energy density. It's not great. But in gasoline engines, you can compress it like a lot, which is important for gasoline engines. So it's pretty good there.
So you're telling me it's in gasoline?
No, but it would be useful. Like if you had a gasoline engine, you could replace it. I should do that. I should put ammonia in there instead of gas and see what happens.
I would wait until you could pay for your funeral bills.
Oh, and here's a cool thing. Hydrogen.
That is a cool thing.
So hydrogen...
Hydrogen's a great thing.
It is pretty good. Hydrogen, you know how it's cool and everything, but you know there's hydrogen fuel cells, right?
Yeah.
Well, a lot of times it's hard to store hydrogen.
The cutting edge.
Because it's like a gas. It's difficult, and you have to freeze it and stuff. But ammonia, you can actually store it like 3 times more dense. And so you could use it as like a storage system for hydrogen fuel cells.
Yeah. Like, closest place you're going to find like a large amount of liquid hydrogen is the center of Jupiter. True story. Center of Jupiter is full of liquid hydrogen.
And doesn't it like behave as a metal?
It's very weird, yeah. We could do it. That's interesting. It's fascinating.
Metal-like. Well, it's because it's basically becomes a plasma, and like the electrons are hopping. It's like a sea of electrons, just like metal.
Yeah, there's
I bet that's probably what it is.
Yeah, there could be people there.
Well, the thing is there's like less. Like, there's less of an atomic force to keep. Or sorry, there's more of an atomic force from the hydrogen. That's probably why it has to be compressed so much.
I mean, it repels more?
No, like, since it's one electron and one proton, the force between those two is extremely strong in comparison to metal. Because metal has, like, so many electrons and stuff, and so many shells that the electrons can kind of float away a little bit.
Yeah, of course.
So, I was thinking, oh, well, I wonder why that would happen. But then I realized it's so much pressure that the electrons get to go free.
Insane. That's, yeah, it's like this. It's almost like the sun.
Anyways, it can also be used in balloons. Like to hold them.
Next time you go out with your get balloons, going out to Party City, I'm gonna make my voice pretty high and just suck some balloon out.
Yes.
And you
breathe in ammonia. Ah ha ha. It wouldn't kill you that quickly, but like
go to the hospital.
How quickly? You know, let's actually see how
there goes
quickly.
There goes Uncle John.
Uncle John.
Beef preservative.
Yeah. You can use.
Is that in those packets in beef jerky?
I don't know if it's in those, but like it's used industrial to kill microbes.
Oh, okay, industrial.
To kill microbes on meat, bacteria and such. It's cool, I guess. I don't know why they do it. It's just it kills bacteria. It does. Don't know why. It's probably because of how reactive it is. It probably like rips some electrons from the bacteria and some of the water and stuff. You know what I mean?
I don't know. No, it's just speculation.
Yeah. And it's also used as a cleaner, of course. If you look at basically window cleaner, anything in your house that cleans except for soap,
over there.
You will see it like on the anything that sprays in your house as a cleaner. You will see it almost always in ammonia, or you will almost always see ammonia in it, and that's because oil is non-polar, which means it does not mix with water. So if you tried cleaning it with water, if you tried cleaning oil with water, you're gonna have some problems.
Well, you already know what happens when oil and water.
Yeah. So, oil can't be cleaned by water, obviously. But ammonia reacts with the oils by taking some of those protons away, and that makes the oils polar. And then now that they're both polar, water and, the new deprotonated oil, they can mix and you can wash it away. And also it leaves a streak-free shine because what's left over after this whole thing is a little bit of ammonium hydroxide, which evaporates extremely quickly. So quickly, so good at evaporating that it's actually used as a refrigerant. Because refrigerants, they require extreme evaporation and condensing, so it's used a lot as a refrigerant.
Well, if you made it this far, congratulations.
You get the I Learned About Ammonia badge.
We'll be producing this, another one of these.
Just throw up a picture right here of the I Learned About Ammonia badge. We're both going at different fields. This is like it's a sphere now.
It's an ammonia sphere.